In our previous lectures, we have studied about dielectrics, electric flux density and electric field intensity. We also derived the Gauss law, where we found that the flux of electric flux density is equal to the free charge density. Now today we will solve a numerical example where we will have a dielectric sphere which is uniformly polarized, and we will try to find out the field inside that sphere. We will be surprised to know that the field inside is constant. So let us see how. Let us say that there is this sphere of dielectric which is uniformly polarized. Since it is uniformly polarized, so we know that the dipoles will be aligned like this, maybe in this fashion. So as we have seen in our previous lectures, that these charges which are inside will cancel themselves, and resultant will be that there will be charges on this surface, like there will be plus charges, let us say like this, on this surface, and minus charges on this surface. So we need to find the electric field inside this dielectric sphere. Now there can be many methods to find this or solve this. One method can be to find the electric field by direct integration by taking these charges, and another method which we will use a trick which we have seen in our previous lectures. What we will do, we will take this dielectric sphere which is uniformly polarized as equivalent to made of two spheres. Let us say this is a sphere of same radius. Let us say this is radius r. So this sphere is also of radius r, and this sphere is, let us say, uniformly charged with charge density given as rho minus, and this center is, let us say, O minus. Now we will take another sphere of the same radius, but its center will be shifted by a length L. So what will happen? The sphere which will be having a center shifted by L will superimpose on this first sphere, and we will have a charge density because of this, like this. So the other sphere, let us say it is having uniform charge density of rho plus. So in fact what will happen, that this rho plus and rho minus will cancel themselves in other part of these spheres, and here only plus charges will be left, and here only minus charges will be left. So you see that this situation is equivalent now. We have seen a similar example in one of our previous lectures. Now you know that the field due to a uniformly charged sphere is given by the charge density over 3 epsilon naught into the distance of the point from the center. So let us say I want to find field at this point P. So from this it will be r plus, that is distance from the center of the positively charged sphere, and this will be r minus, that is the distance of point P from the center of the negatively charged sphere, and this is L. So the resultant field at point P will be field due to the positively charged sphere and the field due to the negatively charged sphere. Now it will be rho over 3 epsilon naught r plus minus rho by 3 epsilon naught r minus. So this will be taken outside. This will be r plus minus r minus. So now from this diagram we can see that this is r minus, this is L, and this is r plus. So you see that L plus r plus will give us r minus. So you see that r plus minus r minus is equal to minus of L. So the resultant field at point P will be minus rho over 3 epsilon naught L. So this is the resultant field. Now we want to have a relation between the uniform polarization. So let us say that this dielectric is having a uniform polarization of P. Now we want to find this relation between this P and this electric field which we have just derived. So let us say that we have a uniformly charged distribution of rho coulomb per meter cube. So let us take a small volume delta V. So charge in it will be rho delta V. Okay. Now if we put some electric field, or this sphere is put inside a uniform electric field, so what will happen? This charge center may shift little bit. Let us say it shifts by a length L. So this will be the dipole moment, total dipole moment. Okay, so dipole moment per unit volume will be, which is same as the polarization vector. So you see that the polarization vector is equal to rho L. So it implies that the field inside a uniformly polarized sphere is constant, and its value is given by minus P over 3 epsilon naught. So this is the resultant field inside a uniformly charged dielectric. Now let us try to draw some field lines. So as we know that there is no free charge, so del dot D will be equal to 0. So it implies that this D is going to have closed field lines since its divergence is equal to 0. We will see a similar property of magnetic field also, and in that we will again see that these field lines make closed loops. So this is a hint which we can see now, that if we want to draw the field lines of this flux density, they will make closed loops. So let us try to draw them. So this is a uniformly charged uniformly polarized dielectric sphere. So you see that the polarization vector will be in this direction. So this is for solid lines, this is polarization vector, and for dotted lines I will show the resultant electric field. So we know that the resultant electric field inside it is minus P naught over 3. So you see that the electric field will be in this direction inside this, and outside this dielectric sphere the electric field will be like this. Although I should have drawn dotted according to the legend, but it is now understood that the field lines will be like this. Now we want to draw the field lines of flux density. So you see D is equal to, I am assuming a linear dielectric, epsilon naught E plus P. So it will be epsilon naught minus P by 3 epsilon naught plus P. So it is equal to twice of P by 3. So you see inside this flux density is having same direction as that of the polarization vector. So we can see that electric flux density will be in the same direction, and outside it will follow the same law, D is equal to epsilon naught E. So the field lines will be similar. So you see that the electric flux density lines are making closed loops. However, the electric field intensity lines are not making closed loops. They are making in this direction outside this shell, this dielectric sphere, and inside this dielectric sphere these are in this direction from plus to minus. So this is the difference. Now you see that although this relation is there, D is equal to epsilon E, but because of its changes inside the dielectric, the direction of these two are totally different, and their values are also different. Now there is confusion in various students' mind that since there is Gauss law that del dot D is equal to rho free and del dot E is equal to rho total, that is rho free plus rho bound. So they think that this D is just because of the free charges and this E is because of the total charges. However, this is not the case. This D as well as E both are influenced because of rho free as well as rho bound. However, their flux is what gives us rho free for the flux density, and the flux due to the electric field intensity give us rho total. So the flux is what it is being given by this divergence, but their own values, they will depend both on the free charges as well as the bound charges. So let us see it more clearly. So let us say there is this external free charge Q and there is this dielectric. So let us say because of this charge Q, dielectric gets little bit polarized like this. So we will make a Gaussian surface. So this is the Gaussian surface. For this Gaussian surface, if I will make E dot ds over this closed surface, it will give us only this q by epsilon naught. However, similarly, this d dot ds, this q plus this q bound, this is q bound. For d dot ds, I will just get q free. So this is the flux which we will get. But the value of E and D will depend both on the free as well as bound charges. Now, let us say I remove this charge. So what will happen? The value of E will change as well as D will change, because D is equal to epsilon E. And now these integrals will just give q bound over epsilon naught, and d dot ds will give 0. So I hope now it is clear that although the flux is totally giving us q free and this is giving us q free plus q bound, but their values are depending on both kind of charges. So this is what we should understand, and we should be pretty clear in our mind. So if you find that this lecture is helpful to you, then please share and subscribe our YouTube channel, and also join us in our Telegram group for doubt discussion, and the link of the Telegram group is given in the description of this video. Thank you.